They sure are. Okay, so as some of you may know, my name is Baginski and I'm a senior here at Lawrence University. And today I'm going to be talking to you about bitter brew and contributions of hop chemicals to beer flavor. Specifically, I want to talk about alpha and beta acids and how they contribute to the flavor of bitterness in beer. So a little bit about history and their hops in use and their use in brewing. Around 4000 BC, Sumerians crafted red beer, and this was entirely by accident, where some baker's bread dough and some yeast from the air and water combined, or at least that's what's hypothesized, and eventually fermented and produced this concoction that was later referred to as this divine drink. And eventually there would be social gatherings where people would end up and drink together this red beer, or otherwise known as beer. And then around 1500 BC, Egyptians medically prescribed beer, as seen from this evidence of this hieroglyphic right here. And then around 100 AD, Romans introduced beer to Europe. And then finally, at around 822 AD, hops were introduced to the production of beer. And there was some resistance with the introduction of hops to beer. Specifically, the English labeled hops as a pernicious weed and banned its use for some time. Then around 1516 AD, German purity law identified hops as one of the main ingredients of beer. And from then on, people use beer regularly. So if you could pass along those hops, you could open it up, smell it, touch them, and I'll describe what hops are. So hops generally belong to the plant family of Cannabiceae, which also includes marijuana. However, for brewing purposes, Cumulus lupus is used to provide those alpha and beta acids in beer. It's a dioecious plant, which means that it has both the female and the male hop flowers on that plant. However, the female hops are preferred since they are generally seedless, and the seeds produce off flavors in the final product of the beer and are generally a hassle to separate from hops themselves. So this is the general structure of a whole leaf hop, and these hops can affect a lot of things in beer. Specifically, they can affect the aroma, or how that beer smells, from the terpenes and essential oils found in the lupulin glands over here. And again, hops can affect the bitterness and flavor by the contribution of alpha acids to that flavor. Then foam stability is also affected, and shelf life is also affected by these alpha and beta acids, since they present antimicrobial properties and actually increase the storage time. And people who drink beer actually tend to have fewer cavities in their lifetime. So now that we've discussed a little bit more about alpha and beta acids, let's talk about their use in brewing. So we can see that alpha acids, humulone, cocumulone, and adhumulone, all structurally look similar, where they have 6-member rings and are generally the same except for this R group right here. And then beta acids, lupulone, colupulone, and adlupulone, share that same property, where structurally they look similar to each other except for this R group right here. And that has to mainly do with the amino acid content of the hop itself. One important thing to mention is that alpha acids are responsible for the bitterness in beer, but they are not what you taste when you drink that beer, since alpha acids are generally insoluble in water, and it's not until a boiling in the brew kettle, in the brewing process, that a thermal isomerization takes place. So what we have here is humulone in an alkaline environment that this hydroxyl then oxidizes and then grabs a proton. And then in this intermediate step is where this 6-carbon ring rearranges to a 5-carbon ring. This mainly happens by a mechanism similar to a benzoic acid rearrangement, where this again this hydroxyl oxidizes and then this carbon 5 rearranges to the carbon 6. And then with that we get the formation of isomerized alpha acids, both the cis and trans product, in a 68 to 32 ratio. And this is exactly what you taste in beer. So, as some of you may or may not know, there is a certain level of bitterness in different styles of beer. And that different bitterness is scaled on a scale, it's on a scale of international bitterness units. And one international bitterness unit is usually equal to 1 milligram of isomerized alpha acids per liter of beer. So since these are just averages of the IBUs of different styles of beers, there is some leniency, more or less, where you can have more IBUs or less. But however, as a brewer, you want to provide a consistent product for your consumers and maintain a consistent level of isomerized alpha acids in your beer and a consistent bitterness in your product. So now that we know that different styles have different bitterness, let's talk about how different hop varieties provide different characteristics to beer as well. There's two forms of hops: whole leaf hops, which are hops in their natural state, and then pelletized hops, which are just a condensed form of whole leaf hops. Pelletized hops are usually more utilized in larger breweries since there is less of a hassle than using whole leaf hops. There's more of a cleaner process with whole leaf hops. And with my research, I looked at 3 different hop varieties: Citra, Sterling, and Cascade. Citra is known to have high alpha acid content and a total oil content, so those essential oils and terpenes. Sterling is what's known as a noble hop, so it doesn't provide much of those alpha and beta acids. In fact, it has low concentrations usually, and it provides more of those aromas. And it's typically called an American floral hop. Cascade hops are balanced in their alpha to beta acid ratio, so they have an equal alpha and beta acid ratio concentrations, and they're typically labeled as American aroma hops. So hops, any raw materials, but specifically hops in our case, are susceptible to aging and oxidation. So old hops actually develop a distinct cheesy aroma as they age. And that's because of the oxidative cleavage of these acyl side chains right here. That oxidative cleavage forms mainly 3 products: isovaleric acid, isobutyric acid, and 2-methylbutyric acid. And I don't know if you're familiar with the aromas of these compounds, but isovaleric acid resembles a smell of a pungent cheese or a sweat odor. And then isobutyric acid and 2-methylbutyric acid actually have distinct smells of vomit-like smells. So typically you can see why you don't want these aromas in your hops. And from a quality assurance and quality control perspective, you want to be mindful of that oxidative cleavage as hops age, since you're also getting a degradation of those alpha and beta acids. So in order to hit a consistent mark of international bitterness units, we want to know exactly how much of those alpha and beta acids we start out with to initially plan out how much hops we have to use so we can isomerize and then get that final bitterness in beer. So there are a couple techniques to analyze those alpha and beta acids. There's a traditional UV-Vis method, where you take toluene and you basically put some hops in it, take that toluene extract and observe it under 314 nanometers. When you take the UV-Vis spectroscopy under 314 nanometers of that toluene extract, there's many interferences of the hops in the hops themselves that also absorb at 314 nanometers. So you would be getting an overestimation of those alpha and beta acids. So we want to successfully separate those alpha and beta acids from other components in hops and accurately quantify them so we know exactly how much alpha and beta acids we are starting out with in our process. And that's through the use of chromatography. So chromatography generally are a set of techniques that are used to separate complex mixtures. And in our case, we're going to be using chromatography and separating by polarity. And if you look over here, this picture, this analogy explains the theory, the principle of chromatography very well. So if you imagine that there are heavy drinkers, which are nonpolar molecules, and social drinkers, which are polar molecules. And then we have a stationary phase of nonpolar stationary phase of bars along a street. Then we can relate this to chromatography, where if you imagine a heavy drinker and a social drinker beginning at the street of bars and at the same time, and they're walking and traveling down, you can imagine that this nonpolar heavy drinker is going to be interacting with those bars much more than that social drinker. That heavy drinker will go to that first bar, leave, probably go back for another drink, go to the next bar, leave, but then go back to that same bar for another drink, leave, go back to that same bar, and as a result, travel much slower down the street. However, the social drinker, the polar molecule, won't interact so much with the nonpolar stationary phase. It will actually go to that first bar, then leave, get another drink at another bar, maybe skip a bar, and as a result, travel much faster. So this introduces another principle of retention time. So if the social drinker is moving much faster because there's less of that there's less of that interaction between the stationary phase, then it has a much lower retention time. However, since the heavy drinker has much more stronger interaction between the nonpolar stationary phase, it has a higher retention time, and it reaches the end of that street much later. And by that technique and analogy, we have separation of our heavy drinkers and our social drinkers, or our nonpolar and polar molecules. So high pressure liquid chromatography relies basically on that technique, except it uses high pressure to push a mobile phase, which is your solvent plus sample, through a stationary phase, which would be our column over here, to separate a mixture into separate components. So if we look over here, here's our HPLC, and here are the solvents that are typically used, and for our case we use a mixture of methanol and water. So the solvents travel through to the pump, and then there's an injection of the sample to the pump as well. They're mixed together, and that is what your mobile phase is. As the mobile phase travels, it goes to your column, which is inside this box here, or column oven, and after that separation occurs, it goes to the detector, and those separate components are analyzed with UV spectroscopy. So HPLC, as you can see, is a rapid advanced separation technique with a rapid analysis time. It has low solvent use because it runs so quick, and very little sample is needed. So this can either be a qualitative technique or a quantitative technique. So we can either see exactly how much of something we have in our mixture, or do we have this in our mixture, a certain substance. So a little bit more about the separation mechanism that occurs in HPLC, and referring back to the bar analogy and the social and heavy drinkers. Our column, which is our stationary phase, is packed with octadecyl carbon chain modified silica. So we basically have modified those silica particles to become nonpolar, just as in the example with the bars, where our bars are those nonpolar molecules. And then we can imagine that the more polar components will be eluted first as a result, just as those social drinkers reached the end of the street at a much faster time. So the separation basically depends on this mechanism of that mobile phase and stationary phase interaction. And if you think back to Gen Chem, where you learn like dissolves like and intermolecular forces, you already know that a nonpolar compound will interact with another nonpolar compound more strongly than a nonpolar compound interacting with a polar compound. As we can see in this example here, our ammonia, our polar compound, or social drinkers, will leave the column at a much faster time, where our hexanes, our heavy drinkers, will be interacting with those bars or those chemically modified silica particles much more, and leaving much later. So here's an example in our data of exactly that. We have on our y-axis absorbance at 314 nanometers and time on our x-axis. And a change in mobile phase can detrimentally affect your separation. as seen here. So first we have our 85% methanol to our 15% water mobile phase, where we see these green peaks. They are nice and symmetrical, sharp, separated, and narrow bands. However, when we look at just a 5% difference where there's 80% methanol to 20% water, we can already start seeing that these peaks start being asymmetrical, and there are humps in these peaks here. All we need to know about that right now is that generally this produces more uncertain quantification. We're less certain when quantifying these type of peaks over here. We don't know if it's an impure compound or if there's other components into it, or it's two peaks, and it has a hump right here of the second peak. So we opted for the 85% methanol and 15% water mobile phase because we want to be more certain with our quantification of those alpha and beta acids. So another flow rate is another factor that can affect the separation mechanism. So you can imagine that with increased flow rates, you'll actually have less time, you'll allow less time for that mobile and stationary phase to interact with each other. So as depicted here, if you have a fast flow rate, those social and heavy drinkers will be eluting at the same time or reaching the end of the street at the same time. And they'll be almost indistinguishable in our data. Another factor that can actually effect that is similar to this is column length, where if you can imagine a much longer column will allow more time for that mobile and stationary phase interaction rather than a small column like this. So here's an example of our data of Stirling brew craft peak shifts with different flow rates. On the y-axis again, we have absorbance at 315 nanometers and time on the x-axis. And we have the same mobile phase for both, 85% methanol to 15% water. However, this time we played around with our flow rate from 0.6 milliliters, and we looked at 0.8 milliliters per minute. And this is how fast that mobile phase is traveling through that stationary phase. So, as we can see, both of these sets actually have nice symmetrical and separated peaks. However, the 0.6 milliliters per minute actually has more separation as a result of that slower flow rate. There's more time for that mobile phase to interact with that stationary phase. So in order to be more certain with our quantification of our alpha and beta acids, we opted for the 0.6 milliliters per minute. Now, we saw just a couple of chromatograms recently, and how we get those chromatograms is with our photodiuretic detector. So this photodiuretic detector provides detection at either single or multiple wavelengths. So it can actually provide a complete spectrum every 12 milliseconds. And with this information, we can actually analyze the purity of certain peaks. So the general schematic of our diode array detector is that a visible lamp source and a UV lamp source travel through a flow cell, which is also where our mobile phase travels through, and then hits a grating, and then hits a diode array where that complete spectrum is produced, and then goes onto the detector where our Galaxy software can translate those results into something we can understand a little more. So this spectroscopy technique actually works on Beer-Lambert's law, where absorption is equal to the extinction coefficient times concentration times the path length. If we imagine analysis of the same compound for multiple runs, we can imagine that the extinction coefficient and the path length will be constant. And then we can also observe that absorption and concentration will have a direct relationship, where if you see an increased absorption in one of your chromatograms of the same component in a mixture, then you will also see that that means that there's an increased concentration of that component. So, as I mentioned before, with our photodiuretic detector, we can actually obtain a complete spectrum of our run. So every single peak actually has every single absorbance for every single wavelength taken. And with this, we can actually take the ratio of two wavelengths across that peak of interest and determine the peak purity. So you can imagine if the ratio stays constant across the two wavelengths, then the peak is pure. However, if the ratio of those two wavelengths, of the absorbance of those two wavelengths changes, then you can imagine that the peak is impure. And this is simply due to the fact that if we assume this is a pure peak, as said here, at different wavelengths, it will have the same absorbance. However, if we assume that this is an impure peak where it has two or more components inside that peak, you can assume that at different wavelengths, those different compounds will be absorbing much more at different wavelengths or much less, therefore leading to a different ratio or a changing ratio across the peak. So here we have an example of a pure peak, which we should expect because this was our standard, our international calibration extract. And running this at 85% methanol and 15% water as our mobile phase, and a flow rate of 0.6 milliliters per minute, we took a look at some of the peaks, and specifically we looked at colloculum. And also y-axis absorbance, x-axis time. Sorry. So looking at colloculum, the Galaxy software actually calculates the purity of the peak of interest. So we can see here that this is a 100% pure peak, where the ratio over here, the purity value is at 1000, which correlates to just 100% purity. However, we can also observe impure peaks within our data. And this is a different method, 80% methanol, 20% water, with a flow rate of 0.6 milliliters per minute. And this is analyzing the stirless and Optimus Rex pellets. So we took a look at this colloculum peak right here. And while it had some medium impurities, which this actually correlated to around 80% or more pure, or 80% to 100% pure, but not completely pure. So, and then we had some more impurities at the tails here. So we typically did not use data like this, and spoiler alert, we didn't use this method for this exact reason, because we would be less certain with our quantification of those alpha and beta acids. So our method that was used to actually quantify these alpha and beta acids is as follows, where we have a mobile phase of methanol, water, and phosphoric acid in 85 to 17 to 25 volume to volume ratio. We have a flow rate, which is again how fast that mobile phase is traveling through that stationary phase, of 0.6 milliliters per minute. And then we're observing detection at 314 nanometers because this is the maximum absorbance for those alpha and beta acids. And this is just the typical chromatogram of one of our standards, the International Calibration Extract. So you've seen a bunch of chromatograms so far, and I wanted to talk a little bit more about the parameters, specifically the efficiency, retention, and selectivity, and how you can manipulate each of these to obtain a better resolution and therefore achieve the best separation and peak quality. So efficiency is actually just indicative of column performance. So you buy a column, it has a certain efficiency with it. And typically, the only way you can manipulate this is if you have more money. And so we can see here, relating the efficiency to this graph right here, the width of these peaks actually is related to the efficiency, where if you have more of a wide peak, you're going to have a much larger number here, and therefore a much lower efficiency or plate number. Therefore, also, if you have a much narrower peak, then you would have a small number here and much higher number here. Retention time is just a measurement of the time that the sample is in the stationary phase relative to that it is to in the mobile phase. And then selectivity is just looking at the separation of two components in the chromatogram. So you can imagine if two components in the chromatogram have the same retention, then you can imagine that selectivity would also be 1. That would usually you can also already assume you have a coelution. There's two components in one peak. And then plugging that into our fundamental resolution equation, we can also see 1 minus 1 will equal to 0, which will have a pretty bad resolution. Overall, we want to achieve a resolution of 1.5 or better, and that would translate to separated peaks and with a nice symmetrical shape. So after we've optimized our method, we want to see what these peaks are. We want to identify each of those peaks. So for known sample components, such as in my scenario, we just use a standard of a pure compound to assign the peaks. And we used an international calibration extract from the American Society of Brewing Chemists to assign each of our alpha acid and beta acid peaks. Then for an unknown sample components, you can either use the mass spectrometer, or you can either fraction off that peak and then identify further with NMR or IR spectroscopy to get a little bit more about knowledge about the structure of the compound, so you hopefully know a little bit more about what you have, and then again reference it back to a standard so you can assign those peaks. Then we want to quantify exactly how much alpha and beta acids we have. We wanted to look at the area under the curve, or the additive absorbance versus time from peak start to peak end. So thankfully Galaxy does this automatically, and we can observe the area under the curve of each of the alpha acid and beta acid peaks. However, I will also note again, for best possible peak integration, we want a high resolution number, at least 1.5 or greater, so we have that separation. We want a symmetrical Gaussian shape, and we want a flat baseline. This will only increase certainty in our quantification of those alpha and beta acids further. So what is our dating telling us? So as Professor Donahue mentioned, I basically have brought this HPLC back to life since it was having some pressure and baseline issues. After fixing it and thinking it's fixed, I want to know exactly, can our HPLC provide us with reproducible results? And is our HPLC sensitive to varying concentrations? So looking at the different hop varieties, Sterling, Citra, Cascade, and our standard here, we can see that each of our peaks, our co-cumulone and our cumulone and adcumulone, and our co-lupulone and our lupulone and adlupulone, all have ilu off the column or come off the column at the same time, establishing that we have reproducibility. We can also see just visually that we have sensitivity to absorbance or concentration of different components. So Citra over here we can see has a much higher peak, and referring back to Beer-Lambert's law, we know that higher absorption, higher concentration. So over here we can already infer maybe that Citra has more of an alpha acid concentration than the rest of these hop varieties, which we've confirmed with our quantification and our calculations. So over here on the bottom we have Cascade, and then Citra hops, and then Sterling hops. And then we have different hop suppliers, so we have Brewcraft, Hop Union, and Optimus Rex for the different suppliers. And then we have our different forms of hop, whole hops and pelletized hops. And we looked at alpha and beta acids across all of these. So we looked at the alpha and beta acid concentrations of our Cascade, and we found that we have a balanced ratio of those alpha to beta acids. They're fairly in line with each other. And then when we look at our Citra hops, we realized we have this huge alpha acid concentration relative to this low beta acid concentration. Then we looked again at Sterling, and it was again a balanced alpha to beta acid ratio. And we can see that again graphically from our plotted alpha to beta acid ratio up here. So after quantifying, we want to compare our how much of alpha acids and beta acids we've calculated to the reported values that their suppliers have provided us with. And we notice there is a difference for all of them. And we can relate this back to the oxidative cleavage of those acyl side chains, or just the oxidation of those alpha and beta acids, where in each of those hop varieties, those forms and suppliers, we noticed that with alpha and beta acids, there was at least 20% or more of the degradation in each of those. Therefore, you can already see why it is important to do initial results on your raw materials and your alpha acids to receive a consistent product in the end. And in fact, if a brewer, for example, was using alpha acids from the recorded values, he would be producing a beer, or she would be producing a beer, that is less bitter than expected. So in conclusion, we can see that Lawrence University is fully functional. Our data is reproducible and we have sensitivity across varying concentrations. Then we know that preliminary and regular quality assurance is necessary because of that alpha and beta acid degradation. Some future work, not for me since I'm graduating, but someone else will hopefully take over. Someone will optimize the IBU analysis of beer itself, and then relate that bitterness you taste when you drink beer to the bitterness of those the scaled international bitterness units. And we want to see exactly if we are missing a certain component of bitterness that's not accounted for. So special thanks to Professor Donahue and Bobby Fleshman for initial help with this project and just help throughout and advice and guidance and everything. And then I want to thank Dave Hall for helping me with my presentation skills and my presentation itself. Then I want to thank the owners and brewers of Stone Arch Brewery and Appleton Beer Factory for their generosity of beer and hops and conversations. Then I want to thank Daniel Martin for letting me steal all the glassware and supplies I needed. And I want to also thank the Andrew W. Mellon Foundation for providing me the funding to buy new HPLC columns, supplies, and solvents. And I also finally want to thank Dr. Patty Aaron from Millicord's Brewing and Research for helping me troubleshoot my solid phase extraction method. Any questions?
So in your results section, where you quantified between alpha and beta acid, how many times did you quantify?
So generally we did 3 extractions and then we did 3 more runs on each of those extractions. So we did basically from 9 or more runs on each of these. Yeah.
Is prep HPLC feasible, or is it just going to be oxidized?
Is what?
Is preparatory scale HPLC feasible in these compounds, or is it oxidation so much more problem?
What do you mean by preparatory scale?
Well, you said yourself that you can use HPLC to both quantitate and separate.
Yeah.
So let's say we wanted to get it up in. Right? So we can use bigger columns and slightly different conditions to actually collect it in the end, and we actually have auto sample for this purpose.
Oh, I see. It's typically just alpha and beta acids would require an inert atmosphere and cold temperatures not to oxidize after separation, if that's what you're asking.
Yeah.
Idea on time scale that you oxidize?
Typically around 2 to 3 years, you're going to have at least 30% or more of that degradation.
2 to 3 years?
Yeah. But however, that's like in a factory somewhere. If you have it in a cold store, then maybe longer.
So it's not a problem.
It's not really that much of a problem, but we have purchased alpha and beta hops just from random suppliers, and we've observed 25% or more degradation in our alpha and beta acids.
Well, I guess I'm thinking about when you talk about trying to identify other compounds that you see in HPLC, right? So with the new acids.
Oh.
In most cases, we might not worry about oxidation. That's what it's saying.
Yeah, no, typically we weren't looking at oxidated samples right in here. We weren't looking at the oxidized products. Yeah. Yeah.
So you said that the hops typically degrade 30% in 3 years or so.
2 to 3 years, something like that.
You observed 20 to 25% difference in the...
From the reported values.
So is that suggesting that they've been sitting around for 2 years, or do you think that they are...
Well, there's different factors that can increase that aging process, where if there's an increase in temperature for somewhere, that'll induce that oxidation, and then it might not even be, it wouldn't take 2 years. You could do it in a day. Yeah.
The different companies that you source the hops
Yeah.
do you know if they were all getting them from the same area, or were they from, like, where they themselves source the hops?
I don't know that.
brief they don't tell you.
It's the fun of making beer. It's made with agricultural products. Beer. They're will help to a standard making the same thing every cup.
Any more questions?
I have a question about instrumentation. Actually, let me ask you about analysis.
Okay.
So whenever you're looking at mixed compounds, you expect these asymmetric non-Gaussian shapes in
Yeah.
your HPLC. Is there any reason to assume that it's not Gaussian when it's a single product? Or is it just natural to assume that it is Gaussian when it is a single product?
Oh, well, that also has to do with, you can also observe that with, if you have a column that's not as efficient as another, you can see something called peak tailing, where it kind of just tilts over. And also the mobile phase can affect that peak tailing as well. So you kind of just have to tailor your method to obtain a Gaussian symmetrical shape.
So, yeah, on that note, what experiment would you do, right, to tell if it was actually two different compounds or just a weird column?
If it's two different compounds or a weird column, you would look at the peak purity. You could look at the peak purity and observe it through that. And then if you know it's not peak purity, then you know it might be another issue, so you'd play around either with your mobile phase and that interaction between stationary.
I think that's a type 2 test, though, right?
No, that's how you do, because that inherently, no, that's how you would do it. I'm gonna argue with you on that, because that does, you're doing, that's a summative Beer-Lambert law, and so if that changes, that peak purity is about that summative Beer-Lambert law.
Well, I guess what I was asking was like, so my question is, if you have two different things co-evolving or not, right?
Yeah.
And so, so if they have different spectra, then that would show up clear as day, right? But
Yeah.
you could imagine having two compounds, similar polarity, similar chromophore, so the spectrum would look the same, but structurally different.
That would be a little more. I understand what you're saying. That would be a little bit more complicated, especially since they're the same chromophore.
So I think all you would need to do is just change the solvent polarity again, right? Keep
Yeah.
them more non-polar and see if you do see two peaks separate or not.
You could do that. However, I mean, that's only considering if it's the same chromophore and absorbing this at the same wavelength the same way.
Yeah.
How long until this is feasible for a small brewery to buy HPLC for this purpose?
I mean, it depends on how much money the brewery has, really.
I'm just curious, maybe if you've seen the catalogs and the numbers.
I don't know. I think our HPLC at the time when we bought it was around 50,000 or whatever, 20.
And the columns,
Columns, typically the better ones run around 700 to 1,000 or more.
And there's lots of cool instrumentation that has like shorter times, ultra high pressures.
Yeah, exactly. There's that. The new cool thing is ultra high pressure liquid chromatography, where there's new ultra high pressure liquid columns.
right? Get with Greg. They want IBU to some of the beers. So talk to Greg.
Okay.
Pass the baton as it were.
Oh yeah. Any more questions?
Let's thank the speaker.